Hello, welcome back to my channel, JBTeguihanon, your engineering and chemistry tutorial. So in this video, we're trying to study multiple evaporators and compressors systems. So we are going to highlight the types of multiple evaporator and compressor systems. So number one, we are going to look for the multiple evaporators at same temperature with single compressor and expansion valve. Okay, in this video, this is what we're going to look at. Let's jump in. So here we have the multiple evaporators in the diagram, and at same temperature. So you have evaporator 1, evaporator 2, evaporator 3, and you will have expansion valve here, and we have one condenser, and we have one compressor. Okay, this is the setup, the sketch of the system. So we have 3 evaporators at same temperature. So the application of this, for example, you will have a building layout. Okay, you will have a layout here like this. Okay, then you divide it into 3 separate space. Okay, you will have your evaporator 1 here, B1 in this room. Of course, you will have a door, right? Like that. Like that. So you will have evaporator 2 here. Evaporator 2. Wait. This is evaporator 1. Evaporator 2 serving this room, and you have evaporator 3. Okay, 3 separate chamber, and then it is connected with pipe. Okay, you will have a unit there installed in the wall, right? It's connected with pipe. Okay, connected to, this is just a single diagram. Then you will have your condenser, and you will have your compressor. Sorry, you have your compressor, then you will have your condenser. So that is the scenario. Then you will have a pipe again, going back there, right, connecting to the evaporator. Of course, you will have expansion valve here. So that's the scenario. Okay, now here's the important is how to draw the pH diagram, because pH diagram will aid us, will help us how to analyze. So here is the schematic diagram. So this is our saturation vapor line. This is our saturation liquid line. Right? Then you have your AP1, AP2, AP3. And then from here, we will have one suction, okay, side of the compressor. This is the discharge. Then as you can see, we'll add QA here. Q added. The refrigerant pipe inside will evaporate and goes this way and go that way up to here. But you will have a P junction here. Same way you will have Q added here. Okay, Q added here, and then all the refrigerants after sensing or after having a heat transfer to the fluid inside the pipe, or sorry, to the refrigerant inside the pipe, the refrigerant, the liquid refrigerant inside the evaporator pipes will evaporate. Okay, goes there to the suction of evaporator here, sorry, of the compressor. Then compressor will add work to the compressor, and it will what? From 1, it will compress with isentropic compression from 1 to 2. Okay, and this is your point 2 at superheated region. Okay, you can plot your enthalpy 2 from this point down. You can plot your enthalpy 1 from this point down, straight down. Right, and then you have it. So the difference of this, suppose this is 0, right? This is H2. This is your H1. H2 minus H1, the difference is this one. And that is actually work of your compressor in terms of mass of refrigerant. H2 minus H1, right? Okay, after that, after the compression, isentropic compression from 2 to 3, your refrigerant travel inside the pipe in the condenser, and in the condenser you will reject heat QR, and your superheated refrigerant will cool down as it goes inside the pipe from point 2 to point 3 till it reaches to the saturated liquid line. Okay, and here it is. From here, from point 2, your refrigerant will flow this way, past the condenser. Eventually it comes out from the condenser, we call it point 3, and it is now liquid, saturated liquid. And in the pH diagram, 3 is there. So from 3, your refrigerant liquid now passes to the expansion valve. It travels inside the pipe, passes through the expansion valve, and get out at point 4, sorry, and it is now here in the pH diagram. It is now at low pressure, and it undergoes the expansion process from 4 to 1. Okay, there will be heat addition. As you add heat, there will be an evaporation that take place to your refrigerant. Your refrigerant will evaporate. Okay, so here's the formula. Your QA, Q1, Q2, and Q3 load of the evaporator 1, evaporator 2, evaporator 3 respectively in tons of refrigeration. Now, the mass of refrigerant required to circulate through the first evaporator is this. Okay, it's common. Mass of refrigerant 2 is equal to 210, that is just the conversion, times Q2 over H1 minus H4. This is in kilogram per minute. So is M3 is equal to 210 times Q3 over H1 minus H4 in kilogram per minute. And then you add them all, you will have mass of refrigerant. And then work done in compressors shall be total mass times H2 minus H1. And then for the power required to drive the compressor, okay, work of compressor, the W divided by 60 will be equal to kilowatt. The unit will be in kilowatt. And then the RA, the total refrigerating effect, will be the total mass M1 plus M2 plus M3 times enthalpy 1 minus enthalpy 4. Therefore, your COP will be RA over W. Substitute the mass, cancel out, and we will have left this, right? And take note that H sub 4 is equal to HF sub 3. Okay, that's all for now in this video. Please subscribe to those who have not yet subscribed. Thanks for watching. Bye for now.